At long last, the final exciting installment of our introductory lecture on base R programming. And this one is mercifully short. We'll be covering lists and very briefly, data frames. So far, we've spoken about atomic vectors and matrices, which are just a special case of arrays. Their advantage is that they're mathematically convenient. Operations are really fast. They make efficient use of memory, and there are some disadvantages. The crucial one is that they can only store elements of one type. Also, their shape has to be rectangular. If you want to avoid these problems, fortunately, I've got a data structure for you. It's called a list. This is what you want to reach for when you need to store data of more than one type, something with an irregular or non-rectangular shape. Indeed, lists can store anything. They can store atomic vectors, they can store matrices in an array, they can even store other lists. And an important special case of a list that will come up when we start trying to do some real econometrics is a data frame. Here are some list basics. List creates a list just like C creates an atomic vector. So here I'm going to create a list called myList, and it will contain 3 elements. The first element is a vector. You heard that right. The first element is a vector. The first thing in my list is the vector true, false, false. The second element is pi, the number pi, which is a built-in constant in R. And the third element is a matrix, the 2 by 2 identity matrix. So a list is just like a bag of lots of things. You can have anything in the bag, and each thing is numbered. So the vector true, false, false is the first element of my list. Pi is the second, and the identity matrix is the third. We can use the function str, str, to tell us what's inside of a list. This is a very handy function, so don't forget to stir. Str of my list returns the following information. List of 3, and it shows exactly what's inside. It shows that the first element is logical. It has length 1 to 3, so it's an atomic vector of length 3, and it shows us the values. It shows us that the second element is numeric, so that's an atomic vector. It doesn't give us a length because there's only one element, and it gives us the value. And finally, it shows that the third element is numeric, and it gives us its dimensions. It's 2 by 2, and it also shows us the elements. Now, lists are a bit more complicated because they are hierarchical. So if we want to access list elements, we have to think carefully. We still use brackets as we did with matrices and atomic vectors, but there's 2 different ways to do it. The first way is single brackets. Single brackets always return a list. Otherwise, they exhibit exactly the same behavior as atomic vectors. Double brackets, on the other hand, extract an object from the list by position. This does not in general return a list. It only returns a list if indeed your list contains other lists. After you extract an object, you can index into it as usual. I realize that's all very vague, so let's look at some examples. First of all, my list 1 to 2. That's going to return elements 1 and 2 of the list as a list. In other words, it's returning a list of length 2 that contains elements 1 and 2 of the original list. And as you can see, that's what we get. We get the vector of logicals, true, false, false, and we get pi. Similarly, my list bracket 3 returns a list. It returns a list containing a single element, namely the third element from my original list, which, if you remember, was the identity matrix. Now contrast that with my list double brackets of 3. That returns a matrix. How can I tell? Well, do you notice how in the first 2 code chunks on this slide, at the very top of the output, there was a double bracket 1? That's what shows me this is a list, because that's actually the first list element. Whereas in the third code chunk on this slide, one that says my list double bracket 3, notice that's not there. All that's happened is it has returned the matrix identity 2 by 2. Once we've returned that, we can access the elements as usual. So at the very bottom of the slide, I have this terrifying looking expression where I first extract the matrix that is the third element of my list, and then I index into it using another set of square brackets to pull out the element in row 1, column 1. Lists can be named. So when you create a list, just as we did with the concatenate function for atomic vectors, we can do with the list command for lists. So here is a list for ERM that contains some information. Lecturer, which is a character information, number of students, and then a vector of TAs from a previous iteration of the class. So we can access these elements by name. If we use single square brackets with the name, it will return a list. And if we use double square brackets, it will return the object that is stored in that place in the list. But there is actually some handy shorthand for the double brackets quote name here. And that shorthand is $sign. So the way that we typically access an element of a list when we want to return the element itself and we don't want to return another list is by using the $sign. So core ERM $sign lecturer pulls out the element named lecturer from my list, which is just an atomic vector of length 1 containing the character string Frank. Data frames are a special kind of list, and they're one that comes up quite a lot in econometrics and statistics with R. They're a special kind of list that is almost like a matrix, but not quite, and they're used to represent tabular data. Each element of the list is an atomic vector. These vectors don't have to contain the same type of information, but they do have to be of the same length. So basically, a data frame is kind of like a spreadsheet. Here I'm going to create a data frame with some ridiculous information about Xerxes, Xanthippe, and Xanadu, their age, their grade, and their favorite color. I can do this using the data.frame command. Notice that this is very, very similar to what we used to create a list earlier on. The difference is going to be that each of the vectors that I am putting together to make this special data frame has to have the same number of elements. So a data frame has a restriction. The restriction is that each of the elements in the list is a vector of the same length, although they're allowed to contain information of different types. So here I've created this little vector of information about some fake students, and you see when I print it out, I get something that looks just like a spreadsheet. A data frame is a list, so if we do type of students, it will return list, and its class is data frame. So we have a kind of a similar relationship here between data frames and lists as we saw with atomic vectors and matrices, that the type and the class can be different. So here a data frame is a list, but a list does not have the class data frame. We can access the elements of a data frame with a kind of a mix and match of all the different selection rules we have used so far for lists and matrices. So for example, we could pull out the element in row 1 of column 2, which is 19. That's the age of Xerxes. Or we could pull out everything in column 2. That would be the ages of all the students. Or we could pull out all the rows, students, comma, and then we could access the column favorite color by name to return blue, red, and orange. We can also use the $sign notation from lists to access particular columns, because the data frame is a list of columns. That's the way to think about it. It's a list of columns. So the dollar sign in this context is going to pull out one of those columns. Here, student's dollar sign name is going to give me Xerxes, Xantippe, and Xanadu. And of course, we can do even more complicated things. So here I have students, bracket, student's dollar sign name, double equals Xerxes, comma. What does that do? Well, that's actually student's dollar sign name is the vector of names, Xerxes, Xantippe, Xanadu. When I take that vector and I double equals it with Xerxes, I am testing whether each of the elements is equal to Xerxes. That's going to return true, false, false, because the first element of name does equal Xerxes, whereas the other two do not. The comma indicates that that selection, that vector of logical values that I'm passing in should be used to select rows. And since there's nothing after the comma, I should say, we're going to get all of the columns. So that unwieldy looking statement actually extracts all the information about Xerxes that we have in our data frame. So why so few slides on data frames? Well, the answer is that they're a huge pain. That last statement on the previous slide is terrible and ugly and confusing. So we're not really going to work much with data frames in this course. Instead, we're going to work with something better, which is called a tibble. A tibble is a data frame with some extra cool features that make it much easier to work with. So we can use much simpler syntax from an R package called dplyr that we're going to learn about next time. But before we go, I have one exercise for you. And this exercise is about the data frame employees.